flange is constant now. Why it's constant is because 15 millimeters as a function of y. Okay. So the flange, the width is 160. The depth is 20. The y bar will be 35 minus by 20 divided by 2. Okay. And then, oh, this is not comma. Pardon me. This is plus. And then we're going to add. Okay. So the web now, okay, you realize there's a left web and there's also a right web. Okay, there's a left web and you have a right web. So this is where you need to have a 2. And then the area that you are going to consider, right, is 15 minus y bracket 15 plus y multiplied by half. Okay. Oh, sorry, I forget the thickness first. So the thickness is 20 millimeters because you have left and right. So this you will have 15 minus y, 15 plus y, and then we just have to multiply by half. Okay. So what this means over here, so this is our, I will write it down individually what it actually means or not. You will be wondering why this is the case. So for the 2 is the left and right web. Okay. Over here, this is the width. This term over here is the depth. This term over here is your y bar. Okay, or including the half is your y bar. Okay. So just to quickly recall why the y bar is equal to half, I think we derive our equation. Okay, we derive, let's see over here. It's not this one. Okay, we derive that the y bar, okay, over here is c plus y multiplied by half. Okay, so this over here is your y bar. Okay, so that's why the depth is c minus y. The y bar is c plus y multiplied by half. That's the only reason. So from here, we can calculate our first moment of area for the flange. So we have 35 minus 20 divided by 2 multiplied 20 minus 160 is equal to 80 times 10 to the power 3. Then plus, right? So you will have 2, so you have 20. Then you have 15 squared. So it's 225. Okay, 225 minus by y squared. Okay, 225 minus by y squared. So this will become 80 times 10 to the power 3 plus by 225 times 20 is equal to 4500 minus by 20 y squared. Okay. So this will be equal to 80 power 3 plus y4500 is equal to 84.5 times 10 to the power 3 minus by 20 y squared. Okay. Now this function that we have over here is in millimeters cube. Okay, so I'll just show you what not to do. Okay, so ideally when you work this, you want it immediately to be in meters to power of 3. Okay, so if to change this to meters to power of 3, this will be equal to 84.5, right, times 10 to the power minus 6 minus by 0.02 y squared. Okay. Now, my advice, as I said, I did not set out a good example. Okay, what do I do now? See, the best thing to do, best practice, is to work with meters. Okay. So why is this a case? Because if not, converting this can be quite confusing. Right? Over here, 84.5 is easy. 84.5 convert to millimeter cube to meters cube. You just times 10 to the power minus 9. For this case, it's not so straightforward. So my sincere advice is to do this, okay? Work in meters, okay? So QZ, Y, so it's equal to 0.16 multiplied by 0.02 multiplied by 0.035 minus by 0.02 divided by 2, and then plus by left and right is 2, okay? You don't change that. 0.02 multiplied by 0.015 minus y, 0.015 plus y, then you multiply by half again. I will move over. Okay. Then you multiply by half. Okay. So this will come out to be 0.02 divided by 2, 0.35 minus, okay, then times over 0.02 times by 0.16. This is good. 80 times 10 to the power minus 6 plus. So you have 0.02 multiplied by 0.015 squared is equal to 225 times 10 to the power minus 6 minus by y squared. Okay, so this will be equal to 225 power minus 6 times by 0.02. Wait, 225 power minus 6 times by 0.02 plus by 80 power minus 6 is equal to 84.5 times 10 to the power minus 6 plus by minus, sorry, y squared. Okay, so this is directly into meters cube. The confusing part is this part. Okay, this is 0.02 and then you have y squared. If you not know, then you will be wondering what must you do. Okay, so the best thing is deal with meters. Okay, don't be less it will be less confusing for all of us, including me. So next we are going to find out the shear stress, okay, as a function of y, right? So the formula is Vy over Izz, right? Qz divided by T. Okay. So now we are going to substitute in the formula. So V is equal to 90 times 10 to the power 3. We know our Qz as a function of y. So it's 84.5 times 10 to the power minus 6 minus by 0.02 y squared, okay, divide by IZZ, which we have, which is equal to what? 5.813. Thickness is twice, and then you have to put in 0.02. Okay, why 0.02? Because this is the web thickness, correspond to 0.02. You have left, you have right, so that's why we have the 2. So I write down here, this is the left and right. So from here, we can calculate our function now, or we can determine our function. Minus 6 divided by 5.813 power minus 6 divided by 2 divided by 0.02. So you get 32.707 times 10 to the power 6 minus 84.5 power minus 6 times by 0.02. 7.741 times 10 to the power 9 y squared. Okay, so that is the distribution equation, right? From 0 to y to 15 millimeters. Okay, now I'm going to show you again, right? Can we get the same, or what will happen, right, if we look at the distribution below the centroid? Okay, let's see what will happen now if we decide, okay, we have done with the top. What will happen now if we have to do the same on the bottom? Okay, so if everything is right, your equation has to be the same. Okay, so let's try this again. Okay, let's try this again. So I'm going to take the same figure. Okay, so what I mean by that is, so we're going to look at the centroid. Okay, not happening. Oh, here it is. Computer a bit slow today. So what I mean by that is, now we are going to consider the bottom part. Okay, so this is the top. Earlier we dealt with the top. Now let's try deriving it from the bottom. And sometimes it can be easier. Okay, and I want to see for you. So when I say from the bottom, this is still our centroid, right? And the centroid is always the datum. And we know that the distance from here to here is 35. And we are aware that the distance from here to here is 65. Okay. So we're going to take the first moment. So the limits we're going to consider now is 0.065 meters y, and we are going to go, also, what am I doing? So 0 meters y and 0.065 meters. Okay, so you ask me, Eugene, then now where is our y? Okay, so if this is the area, or this is where your y is, for example, this is our y now, right? Then this, so this is the area that you want to consider. Okay, so this is our analysis direction again. So the analysis will start from y max, yes or no? Right, furthest distance away from the centroid. that is the area that you're interested in. So this will be your, so the distance